Given that we know now what is the working of this algorithm, we have to prove that given any graph, it's going to find us the minimum spanning tree. Okay, so it's called the proof of correctness. We already did some in the earlier modules. As I said, the last assignment is going to be on this. Now we have everything to be done online, so I plan to post it as a quiz online. It's a time quiz, most likely. I'll decide and post the instruction for doing the quiz. So we have to, again give you a reading list of theorems and properties to read, and you can be prepared. And once you can take the quiz only once. So once you log in, you have to, or start the quiz, you have to do the quiz and complete it. Okay, so how are we going to prove this algorithm is going to do what it's supposed to do? Alright, so we are going to use the approach of proof by contradiction. So you know what proof by contradiction means from the earlier examples or modules you have seen. So here what we have to prove is the Kruskal's algorithm is going to find a minimum spanning tree. So let us say T be the spanning tree found by Kruskal's algorithm. We have to prove that it is a minimum spanning tree, right? So we'll assume some contradiction or kind of an opposite thing, that T is not a minimum spanning tree. There exists some other tree, say T prime, that is found by some other hypothetical algorithm or hypothetical approach, and that's a minimum spanning tree. Okay, so again, when I say this T found by Kruskal's is not a minimum spanning tree and T prime is a minimum spanning tree, then what does it mean? The weight of T prime, the weight of T prime means the sum of the edges, edge weights on this T prime is less than the weight of T, right? Because of course, for compared to any spanning tree, the weight of T prime is less than, because it's a minimum spanning tree. So in our case, this T found by Kruskal's algorithm is of weight of W of T, and the tree T prime found by hypothetical algorithm is of weight W of T prime. So we'll start with by assuming that the weight of T prime is less than the weight of T. So now we have to kind of argue or explore whether this is really possible. Okay, all right. So now we should also kind of be able to find out that since weight of T prime is less than weight of T, there are two different spanning trees, right? Because if both T and T prime are the same spanning tree, means all the edges part of the spanning tree are the same, then the weight of T prime will be equal to the weight of T. So the reason that weight of T prime is less than weight of T means the two spanning trees have different edges. Of course, the number of edges should be the same. So if here you have 6 vertices, so it should be 5 edges part of the spanning tree and 5 edges part of the spanning tree. But the edges, the actual edges could be different or need to be different, because the weight of T prime is less than weight of T. Now what I say is that in that case, that means there should be at least one edge difference between T and T prime. So what I mean by edge difference? So an edge difference means there should be one edge, say like this E, which is in this tree T and not here, and there should be an edge E prime which is in this T prime and not here. So that is meant by an edge difference. An edge E which is in one tree, not in the other tree, vice versa, an edge E prime that is in one tree and not in the other tree. You see, in this example, all the other edges are in both the trees. This edge is there in both the trees, this edge is there in both the trees, this edge is in both the trees, and this one is also there. So the number of edge differences between T and T prime is 1, because there's only one edge here that is not here and vice versa. So it's called one edge difference between the two spanning trees. If we have another edge that is in one tree and not in the other tree and vice versa, that is considered to be like another edge difference. So in that case, we'll have two edge differences. So in this case, we have only one edge difference between the two trees T and T prime. Okay, all right. Now, so what I'm going to do then is I'm going to remove this edge E in this tree T formed by Kruskal's algorithm. So when I remove it, it's going to Or let me do the other way. Let me backtrack. I'm going to remove this e prime. So I'm going to remove this e prime in the t prime. Okay, so let us do that. So I'm going to remove this e prime from t prime. So that's going to disconnect the t prime into two components like this, right? Okay, so now what edge I could use to connect these two components? It could be e prime or e, right? Because from the two spanning trees we find that there are at least two edges e and e prime connecting the two, possible to connect the two components. Now if it was Kruskal's algorithm's choice to pick an edge to connect the two components, Kruskal's algorithm, the algorithm that we just went through, would have picked what? This edge E to connect these two components, because the weight, because what? If Kruskal's algorithm found this spanning tree, right? So Kruskal's algorithm picked E instead of E prime to connect these two components. And so if Kruskal's algorithm picked E instead of E prime to connect these two components, it means the weight of E should have been less than or equal to the weight of E prime. If weight of E was greater than the weight of E prime, Kruskal's algorithm would not have picked E, it would have picked E prime. The reason you find E as the choice of Kruskal's algorithm to connect these two components is because it would have been like what? Weight of E is less than or equal to the weight of E prime. So if that is the case, from T prime we could as well remove E prime like we just did and add E to connect the two components and get a new spanning tree, which will be same as T, because of course there's only one edge difference. By doing this edge change, we are reducing the edge difference from one edge difference to zero edge difference. So the resulting new tree, right, would have what weight? Since the weight of E is less than the or equal to the weight of E prime, so it is like this. You are starting with T prime and removing what? E prime. E prime is a larger edge weight, right, because weight of E is less than or equal to weight of E prime. So from T prime you are removing an edge of larger edge weight and adding an edge of smaller edge weight because it's less than or equal to. So the resulting spanning tree will be of a smaller edge weight. So let us pick some numbers. Let us say weight of E is 5, weight of E prime is 10 and weight of T prime is say 30. So 30 minus 10, removing a larger edge weight. So the new the sum of these edges here is 30 minus 10, 20. Then you are adding E, a smaller edge weight, 5. So 20 plus 5 is 5. So the 25 is less than this 30, that was the weight of the spanning tree to begin with, right? So by doing this edge swap, or in the process of reducing the edge difference by 1, we were able to reduce the weight of T prime to something less than or equal to the weight of T prime, because in the worst case it could be equal, right? Weight of E is equal to weight of E prime, so that's why this equal to comes again. But in general we can say like this. So from T prime we removed an edge of larger weight or less than or equal to greater than or equal to this E and added an edge which is of weight less than or equal to E prime, right? So that means what? T prime cannot be called a minimum spanning tree to begin with, because it is possible to even reduce the weight of T prime from what it is or what it was to begin with, right? So that's a contradiction. If T prime was a minimum spanning tree to begin with, we should not have been able to reduce its weight further. But by doing this edge change, we have shown that it is possible to reduce the weight of T prime further. By removing E prime and adding E, we have shown that the weight of T prime could be reduced from what it was before. So that's a contradiction to our assumption that T prime is not a minimum spanning tree. Now, as part of this process, you should also realize that by removing E prime and including E to T prime, we have made T prime to become what? Essentially T. And what is T? T is the tree found by Kruskal's algorithm, right? and the weight of this modified t prime, which is essentially t, is going to be less than or equal to the weight of t prime to begin with, right? Because we removed a larger edge weight and added a smaller edge weight. So this is for like t and t prime have one edge difference. Now the same procedure could be applied if this t and some t prime has more than one edge difference. We could reduce the edge difference one at a time from two edge differences. Basically, now we are from one edge difference we are reduced to zero edge difference, right? So we could do the same thing by removing another edge which is not in t but in this t prime or this modified t prime, and adding the edge from t to connect the two components. So you are trying to basically make the hypothetical spanning tree approach to become the Kruskal spanning tree. So, and as part of this process, you are only reducing the weight of the hypothetical minimum spanning tree even further, and make the weight approach the weight of t. Like in this case, we made the weight of t prime approach the weight of t, which means reducing it further. So that means there is nothing that is smaller than t. Everything, all the spanning trees we could come up with as hypothetical spanning trees are going to be of weight only larger than or equal to that weight of t. There is nothing that is going to be smaller than the weight of t found by the Kruskal's algorithm. Okay, so this is how you prove the correctness of this theorem. Now I have given the explanation here. You can go through it. Okay, so I really encourage you to go through it immediately after the lecture. Along with this video, you can listen and do it. So that's one advantage you have now. You can listen to the video several times. Now let me repeat it quickly as a summary. So what you want to prove is the correctness of Kruskal's algorithm, that the tree found by Kruskal's algorithm is indeed a minimum spanning tree. So we will assume the contradiction or opposite, that the tree formed by Kruskal's algorithm will simply a spanning tree. It's not a minimum spanning tree. So let it be simply some tree T, and let there be some hypothetical algorithm that has come up with a minimum spanning tree T prime. So we are assuming that the weight of T prime is less than the weight of T, because T prime we are claiming as a minimum spanning tree and T is not a minimum spanning tree. So weight of T should be greater than the weight of T prime. Now since they have two different weights, that means both T and T prime are not the same spanning trees. There should be at least one edge difference between them. Like here, an edge E that is in T and not in T prime, and vice versa, E prime that is in T prime and not in T. So we are going to now go through a process of reducing the edge difference. So here the two trees have an edge difference of 1, so we are going to make them to have an edge difference of 0. And how are we going to do that? Remove an edge that is in T prime and not in T, and trying to bring an edge from T to be part of this T prime. So that's what we are doing here. Remove this E prime, that's going to disconnect T prime into two components like this. So now we are going to try connecting the two components using an edge that is part of T, and the edge that is part of T connecting the two components is E. So let us connect the two components using E, and this is now the modified T prime. Now what's going to be the weight of this modified T prime? It depends on the edge weights of E prime and E. So the reason, now we can claim that the weight of E is less than or equal to the weight of E prime, because E was edge used by Kruskal's algorithm to connect these two components, and Kruskal's algorithm always picks the edge with the smallest edge weight connecting the two components. So the weight of E will always be only less than or equal to the weight of E prime. So from the original T prime, we removed E prime and added E, and the weight of E is only less than or equal to the weight of E prime. So we removed some larger edge weight and added a smaller edge weight. So the weight of this modified T prime is going to only get less than the weight of T prime. It cannot become more than the weight of T prime. So that means we are able to even reduce the weight of T prime from what it was before. Okay, but remember T prime was assumed as a minimum spanning tree. and we have shown that it is possible to reduce the weight of T prime even further. That means what? T prime is not a minimum spanning tree to begin with, it's a contradiction. And by doing this process of reducing the edge difference, we have made T prime to only approach T, because this is same as T, because the edge difference is now 0. So in general, we can repeat this process by reducing the edge difference from any number all the way to 0. And by doing this, what we are making, so we are removing an edge in T prime that is not in T and adding an edge from T to connect the two components. So we are making all those modified spanning trees to eventually approach to that of this spanning tree formed by Kruskal's algorithm, and every time you're reducing edge difference, the weight of the spanning trees only get reduced and eventually approach that of the weight of the tree formed by Kruskal's algorithm. So that means the weight formed by Kruskal's algorithm is the lower bound. That's the minimum weight spanning tree, and everything else can be only above that if possible, not below that. Okay, so that's the proof. So I'll stop for a minute and store this video.